this video, we're going to talk about exponential functions. So the learning targets for this video are we're going to be able to identify and write exponential functions, and we're going to be able to determine the decay factor or growth factor for an exponential function. Before we get started, as a reminder, the general form for an exponential function is y is equal to a times b to the x power, where b is the base or the growth rate. So b is the growth rate, and a is the initial amount. And you can remember that from the a in amount and the fact that this is a base. Remember the b from there. It's the growth rate is b, and the initial amount is a. So if I have these functions 1 through 4, I'm going to decide, just looking at them, are they growth or decay? And this is a review from the last thing that we did, or the last lesson that we did. So I'm going to look at what my growth rate is, and that's how I'm going to determine if it's growth or decay. As long as I have an initial amount that is positive, so as long as the initial or the a is positive, I know that if I have an absolute value of b less than 1, I have decay, and if I have an absolute value of b greater than 1, I have growth. So exponential decay if it's less than 1, exponential growth if it's greater than 1. So I'm going to look at my growth rate in each of these. So I have my growth rate for the first one is 1/2, which means that this is since the absolute value of b is less than 1, I know this is decay, and a is positive. It's positive 1. For the second function, I have f of x is equal to 10 times 3.5 to the x power. So I'm looking at the growth rate here, and the growth rate is 3.5. That's my b, so since b is greater than 1, I know this is growth. And I know that only because my a is positive. If I have positive a and a growth greater than 1, it's growth. Or a growth rate greater than 1, it's growth. For 3, I have f of x is equal to 0.4 times 1/3 to the x power. I'm looking at my growth rate here. My growth rate is 1/3. So I know that because a is positive, I have, and b is less than 1, the absolute value of it, it's decay. For number 4, I have f of x is equal to 4 times 3/2 to the x power. This is may trick you because it's a fraction, but this is a fraction that's greater than 1. So because the absolute value of b is greater than 1, this is growth. I want to know, what does 10 represent in number 2? I already said it. 10 in number 2 represents the initial amount. So it's the initial amount that you start with. And that's always what the coefficient for that base raised to the x power is going to be. All right, now number 5, I'm looking for, one of the tables represents a linear relationship, one represents exponential growth, and the other represents an exponential decay. I want to label each table correctly, one of those 3 things. So I'm looking at the first table. The first table, I'm looking at my x's first. I'm seeing that my x's are growing by 1 each time. So I'm looking for the growth in my x's and my y's. What's the pattern? This is true for all of the tables. So I know as I grow, for my x's, for all tables, I'm growing 1 each time from ordered pair to ordered pair. For my y's, for the first table, I want to look for a pattern between 6 and 9, 9 and 12, and 12 and 15. That pattern is that I'm adding 3. I'm adding 3 each time as I go from number to number, or y to y in each ordered pair. So 6 to 9 is adding 3, 9 to 12 is adding 3, 12 to 15 is adding 3. This is a constant rate of change. As I increase 1 for x, I'm increasing 3 for y. So this is a linear relationship since it's constant growth. So it's a linear relationship. For the second table, I'm looking for the pattern in my y's. How am I changing as I go from y to y? 56 to 28, 28 to 14, 14 to 7. I can tell that I'm decreasing, but I'm not subtracting by the same amount every time, because 56 to 28, or 56 minus 28 is not the same as 28 minus 14, which is not the same as 14 minus 7. So I'm going to try division instead. Can I find a pattern with division? Well, 56 divided by 2 gives me 28. 28 divided by 2 gives me 14. 14 divided by 2 gives me 7. So what I'm doing is dividing by 2 each time, or I'm going to talk about this in terms of multiplication. So I'm actually multiplying by 1/2 as I go from ordered pair to ordered pair for y. So I know that because this represents my growth rate, and my growth rate is b, if b is less than 1, I know this is decay. So this is exponential decay. For the third table, I'm the pattern from 6 to 9, 9 to 27 over 2, 27 over 2 to 81 over 4. I know that I'm increasing by something each time. I'm not adding something consistently. It's not a constant rate of change, so it must be multiplication since I'm increasing. I can find what I'm increasing by. Take 9, divide by 6. If I do that, 9 divided by 6, I get 3/2 if I simplify. So if I multiply 6 times 3 over 2, I get 9. I can also see that if that's hard for you to think about, you can also look at the fractions. It might be easier for you to look at the fractions. 27 over 2 times what gives me 81 over 4? Well, 3 in the numerator, 27 times 3 gives me 81, and 2 times 2 gives me 4. So I can see that the growth rate that way as well. And I can tell, since that growth rate, or that b, is greater than 1, I know this is exponential growth. That's exponential growth. All right, the next thing I want to do is I want to write equations of an exponential function passing through a set of points. So if I'm given 2 points, I want to be able to create a function that both of the points fit. So if I'm given the 2 points, 2, 5 and 3, 10, what I want to do is I want to create a system of equations, just like when I had 2 points given to me for a linear relationship, and I wanted to find the function that fit both. I would create a system of equations and then I would solve. So I'm going to do that here too. What I'm going to do is, what I know is my x and y, and I know that the general form for an exponential function is y is equal to a times b to the x power. So this is what I know. I know my x's and y's for each of these ordered pairs. So I know in the first pair I have x is 2 and y is 5. And I'm going to take 2, 5, and I'm going to write a function, as much as I can of a function, with that x and that y value. So I know, using this general equation, I can say, well, 5 is equal to a times b to the second power. Since x is 2 and y is 5, I just plugged in x is 2 and y is 5. I don't know my a and b yet, but I'm going to also create a equation with 3, 10, and then hopefully I can combine the two equations somehow to figure out what my a and b is. So for the second ordered pair, I have 3, 10. I know that I can write the function 10, that's y. So instead of y, I'm putting 10 is equal to a times b to the third power, since x is 3. So I'm just replacing the y with 10 and the x with 3 in that general form. Now I have two equations with two missing variables. So I have two equations with two missing variables. I don't know a and I don't know b. I can't solve when I have two missing variables, but I can solve when I have only one. So what I want to do is somehow combine this system of equations, combine these two equations, or cancel something out by combining these two equations. So one of the variables, a or b. And when I was doing a system of equations with linear relationships, I added or subtracted the two equations from each other to eliminate one of the variables. In this case, since we're talking about multiplication instead of addition and subtraction like we would with linear relationships, it's probably not going to be adding and subtracting. But if I added the If I added the left hand sides together and I added the right hand sides together, I would get 15 is equal to ab cubed plus ab squared, since they're not like terms, and that's not going to help me. I didn't eliminate anything, so that doesn't work, which means subtraction doesn't work. If I do multiplication, I'm going to have 50 is equal to a squared b to the 5th power. It's still two variables, not going to help me. So I want to try division. So I'm going to divide the top function by the bottom function. So the left-hand sides, I'm going to divide those, and then I'm going to divide the right-hand sides. And when I do that, I can see right off the bat, without doing anything, that the a and the top and the bottom are going to cancel each other out on the right-hand side. So I am eliminating one of the variables. This is what I want to do. I want to divide the top function by the bottom function. And when I do that, the a's cancel out. On the left-hand side, I get 10 divided by 5 is 2. And on the right-hand side, I have b cubed divided by b squared. And if you have the same base on the top and bottom of a fraction, what you're going to do is take the exponent in the top and subtract the exponent in the bottom, and that's going to be what you're raising b to. So b to the 3 minus 2 is what I actually have here when I divide, and I'm going to get that's b to the first power, and I can just write b. I don't have to write b to the first power. So I know b is 2. If I combine these two equations, eliminate the a's, I get b is 2. So b is 2 for the equation that works for both of these points. Now I'm going to take that b and I'm going to plug it into one of my equations, either this top one or the bottom one, and I'm going to solve for what a is. So I'm going to use the bottom one. I like to use the equation that has smaller numbers. You don't have to, you can use whichever one you want. It'll give you the same answer, but I have 5 is equal to a times b squared. I'm going to plug in, now I know b is 2. So I'm plugging in b is 2. I'm going to have 5 is equal to a times 2 squared. And I know that's 5 is equal to a times 4. I'm going to divide both sides by 4 to solve for a, and I get a is 5/4. So a is 5/4. I know my initial value. This thing is killing me. I know my initial value. I know my growth rate. I can fill that into this general form. So I have y is equal to 5/4 times 2 to the x power. And that's my function that fits both of those points. All right, for the next example, I have 2, 2 and 4, 32. I'm going to start with on top because I know I'm going to be dividing the 2. I want to start with the ordered pair that has the bigger x value, and that's the second ordered pair. So I'm going to start with this one. 4, 32, and I want to do that because I want the higher power to be in the numerator, so I make my life easier because I don't want to divide b squared divided by b cubed. So I want to start with the one that has the bigger x value, and that's going to give me 32 is equal to a times b to the 4th power if I use this general form and fill in my x and y. Then I'm going to take 2, 2, and I'm going to create an equation with that, so I have 2 is y, and x is 2. Or y is 2, and x is 2. Plug those in. I'm going to divide the top function by the bottom function to cancel out the a's. So the left, when I divide 32 divided by 2, I get 16. On the right, I have b to the 4th power divided by b squared, so that's b to the 4 minus 2 power, which is b squared. I'm going to take the square root of both sides to solve for, I just want to know what b is, and that gives me b is 4. Now b can't be -4, so I'm only doing the positive. B is 4. And then I'm going to plug this b in to one of the two equations. I'm going to use the easier one, so that's 2 is equal to a times b squared. So that's 2 is equal to a times 4 squared, because b is 4. Oops. And that gives me 2 is equal to a times 16. I know if I divide both sides by 16, I'm going to see that a is equal to 1 over 8. So I have a is equal to 1 over 8. This is my initial value. B is my growth rate, which is 4. I'm going to plug this information into the general form. So I have 1/8 times 4 to the x power, and this is my function. I want you to pause this video and try the third one on your own. All right, what you should have done was you should have realized that dB is bigger in the second ordered pair, so this is the one I'm going to put on top. So I'm going to do 3 comma 64 gives me the equation 64. So y is 64 is equal to a times b to the third power. So x is 3. And then you take the second ordered pairs, so you have 2 comma 256, and you create another equation. You're going to have 256 is equal to a times b to the second power. You're going to divide the top function by the bottom function to cancel out the a's. And you're going to end up with, when you do that, on the right-hand side, you'll have b, so b cubed, minus b squared is b to the 3 minus 2 power, which is b to the first power, which I just have to write b. And then 64 divided by 256, I can simplify because 64 goes into 256 perfectly 4 times. So I'm going to have 1 over 4. So b is 1/4 is what you should have gotten. And you could have also had 0.25, which you might have had. That's fine. You can write it as the decimal. And then I'm plugging in 1/4. So I'm going to have 64. I'm going to have 64 is equal to, I'm just going to pick the top one to use. I have 64 is equal to a times b cubed. I'm plugging in b is 1/4. So b is 1/4. And then when I do this, I'm going to have 64 is equal to a times 1 over 64. I'm going to multiply by 64 on both sides, because technically I'm dividing a by 64, so when I cancel out that dividing by multiplying by 64 over 1, and I'll get a is equal to 64 times 64, which is 4,096. So 4,096, that's my starting value, or my initial amount. I have my initial amount, I have my growth rate, so I have y is equal to 4,096 times 1/4 to the x power is the function that fits both of those ordered pairs. On the second page, we're going to apply our knowledge to word problems. So for number 1, scientists just discovered a new kind of species of ant. The scientists estimate the population of ants is currently 1,200. The scientists also estimate that ants are reproducing at a rate of 2.4% per month. I want to write an equation that models the growth of the ant colony. So first thing I want to know is what's the initial, I know this is an exponential growth problem because we're doing exponential functions. So I'm looking for the initial amount. That's what my a is going to be. So I'm looking for the initial amount. And that is, in this case, 1,200. That's how many ants I start with. So 1,200 is the initial amount. And then I want to find what's the growth rate. So I want to know what's the growth rate. The growth rate is b, in the function y is equal to a times b to the x power. This is the base formula for exponential function. So I have growth rate is, in this case, I want to look for if it's decreasing or increasing in word problems. So I want to look for words that mean increasing or decreasing. In this case, I see the word reproducing, which means to increase. And then I see it's increasing, so I know it's growth, at 2.4% per month. So when I have a percent that's given to me, to find the growth rate or to find what b is, so if I have growth, right, I'm going to convert this into decimal form and add it to 1. So 1 plus 0.024 is what I have for what b is, and in this case it's 1.024. So I have my b and I have my a, and I'm going to plug them into my formula here, and I have y is equal to 1,200 times 1.24 to the x power. So 1.024, I'm sorry. And this is my answer. For the second problem, Alma decides to get in on the Bitcoin phenomenon. She purchases 1 Bitcoin currently valued at $800 US. Alma heard that Bitcoins are increasing by 75% each month. So first thing, we know this is an exponential function that we're going to use to model it. model this situation, we need the initial amount. So the initial amount is going to be 800. It starts that Bitcoin is currently at $800 where Alma is starting her investment, so 800. And then I know that the growth rate, which is B, is going to be, well, first I'm looking if it's increasing or decreasing. Bitcoin is increasing. It was increasing ridiculously. And it says increasing, so I know this is growth and not decay. And then it is by 75% each month. So to find the growth rate, I'm going to do 1 plus the decimal form of this percent, so that's 0.75. So I have 1.75 is going to be B. I plug those into my formula, so I have y is equal to 800 times 1.75 to the x power. And this is my formula to represent Alma's investment. For B, I want to use this model to find how much money will Alma have in 6 months. So 6 months, this is the time. Time is x, so x is equal to 6. Wait, I'm sorry. Oh yeah, because 75% each month was given to us. Usually it's years, but this is in months, so I know x is equal to 6 since I'm talking about per month here. That was the growth rate in terms of per month. So I have time is 6, so I'm going to plug x is 6 into this formula. 800 times 1.75 to the x power, which is 6, my bad. So 1.75 to the 6th power, if you do that in your calculator, gives you 1.75 to the 6th power is 28.72. So 800 times 28.7229, etc. And that gives me, it is $22,978.32. So when you have money, you want to round to the nearest hundredths place, because that's how we do it with dollars. We round to the nearest penny. Okay. All right. Next problem, number 3. Your club is collecting socks for a homeless shelter. The amount you collect is doubling every 2 days. If you have collected 28 pairs so far, how many would you have in 70 days? So this is exponential. It's going to be an exponential function that I use to represent this. I need to know the initial amount. So the initial amount is going to be, which is A, is going to be 28. So 28 pairs so far, it says, that we've collected. And then the growth rate. So the growth rate, which is B. This is so hard. The growth rate, which is B, is, I know I am doubling. So I'm doubling. If I see the word doubling, I know the growth rate is equal to 2. So B is 2. But I have one more thing here to keep in mind. It's doubling, not every 1 day. So it's not every 1 unit, but it's every 10 units. So it's every 10 days. So I want to keep in mind that the time period, so I'm going to call this a time period, is 10. So it's every 10 days, every 10 units, not 1 unit. We've been talking before about just like 1 month passing by. But now it's 10 for every time it doubles. So we're going to do this just a little bit differently. We're going to write y is equal to 28, our initial value, times. We have 2 raised to the x power, except this exponent represents the amount of time periods. So the amount of time periods that have passed by. And usually we're just talking, it would be doubling every 1 unit, but since now it's every 10 days, I know the time period is whatever x is, however many days have passed by, divided by 10. So I'm going to actually divide in the exponent the time period, which is 10. This makes sense because if I wanted to find how many time periods have passed by in 70 days, I would take 70 and I would divide by 10. And that would give me 7 time periods have passed by. 10 days have passed by. So this is always going to be the case when you have like half-life questions or anything that specifies a time period that is not 1 unit. You're going to divide it in the exponent. Divide it x by that. And this is the formula we're going to use. So we're going to plug in 70 days is our time that's passing by. So we have y is equal to 28 times 2 to the 70 divided by 10, which is y is equal to 28 times 2 to the 7th power. So if you do 2 to the 7th power times 28 in your calculator, you're going to get 3,584 socks. For number 4, the element zinc has a half-life of 243.9 days. You currently have 200 milligrams. How much zinc is left after 365 days? I want you to pause this video and try this problem on your own. You should have used an exponential function to represent this situation. So for exponential functions, we need the initial amount and the growth rate. And the initial amount in this case is going to be, I'm starting with 200 milligrams, so it's 200. And I know the growth rate, or B, is 1/2 because I see the word half-life. So if I see the word half-life, that means it's cutting in half every however many days. So in this case, it's every 243.9 days. It's cutting in half, so I'm multiplying by 1/2. Whatever I had initially, I'm going to multiply by 1/2 every 243.9 days. Here, for example, this is not 1 unit again. This is every 243.9 days. So I also need to talk about the time period. So the time period here is 243.9. Why do I keep doing that? All right, so now what I'm going to do is I'm going to fill this information into my exponential function, which is, so I'll have y is equal to 200, the initial value, times 1/2, times 1/2 to the x. And in this case, because it's not every 1 day, it's every 243.9 days, I'm going to divide whatever number of days have passed by 243.9 to find the number of time periods that have actually passed by. And so, in this case, I'm plugging in 365 because that's how many days have passed by. And I'm going to have y is equal to 200 times 1/2 to the 365 divided by 243.9. This is going to give me y is equal to 200 times 1/2 to the 1.4965, and 1/2 to the 1.4965 power times 200 is going to give me, I'm just going to round to the nearest hundredths place, 70.88 milligrams. And that's how much I'll have left of zinc, which makes sense because it's less than this, and it's a little bit less than half. And 365 is a little bit more than 1 time period. I have, we're just going to review graphing real quick. So if I have y is equal to 1/3 to the x power, I'm going to fill in this table here. -3, I'm going to plug that in. So I'll have y is equal to 1/3 to the -3rd power. And that is actually 3 to the +3rd power, which is 27. So if I have a negative exponent, I do the reciprocal, the base is the reciprocal to the positive of that, and it's 27. So I have 27. Then if I do -2, I have y is equal to 1/3 to the -2nd, which is actually 3 to the +2nd. So the reciprocal of 1/3 to the +2nd. And that's 9. And then for -1, y is equal to 1/3 to the -1 power is the same as 3 to the first power, which is 3. And then I have 0. Anything raised to the 0th power is 1 if you forget, so it's just 1. And then for 1, if I raise 1/3 to the first power, it's just 1/3. And I'm going to graph this. So I'm going to label this graph myself. I'm going to start with, there's something on my screen, sorry. I'm going to use this bottom. So this is going to be my, what am I doing? I'm going to label this graph. So I'm going to start with 0 here, and then I'm going to do 5, 10, 15, 20, 25, 30, 35. And then on the other axis, I'm going to count by 1. So this 1, 2, 3, -1, -2, -3. I'm just going to erase this. My eraser's too big. 1 and -1. All right. And then I'm going to plot these points. So I have -3 and 27, which is up here. I have actually I'm going to do this in red. -3 and 27. I have -2 and 10. I have -1 and, 9. -2 and 9. I have -1 and 3. And 0 and 1. And then 1 and 1/3. So it's not perfect. I'm going to connect these points now. Whoops. And my exponential graph is going to look like this. I am getting closer and closer as I increase the x values. I'm getting closer and closer, but never touching the y-axis. So I'm going to put, the x-axis. So my asymptote is y is equal to 0. And then for number 6, I have y is equal to 2 times 3 to the x power. So I'm plugging in these numbers here. For x, I'm going to have y is equal to 2 times 3 to the -3rd, which gives me 2 times 1/3 to the +3rd power. And that is 2 over 27. So 2 over 27 for this one. -2, if I plug that in, is 2 times 1/3 to the +2 is equal to 1 over 9 times 2, which is 2 over 9. And so this is 2 over 9. -1, I'll have 2 times 3 to the -1st power, which is 2 times 1/3 to the 1st power, and positive 1st power, and that is, so this is 2/3. Then 0 is going to give me 3 to the 0th power is 1. 1 times 2 is 2, so this is 2. And then 1 is going to give me 2 times 3, which is 6. 3 to the 1st power, 6. And then I'm going to plot these points. So again, I'm going to count by 5s, 5, 10, 15, 20, 25, 30, 35, and then -1, -2, -3, 1, 2, 3. And then I'm going to plot these points. So -3 and 2 over 27, which is like right here, so close to that line. And -2 and 2/9, just a little bit farther away from that line, but still very close. Can't really see a difference between these. And then based on the scale that we created, and 0 and 1 I have, 0 and 1, and then I have 1 and 6. I guess that's all I have. I don't have anything else. I'm going to connect these, and the way that it's going to look when I connect them is I'm never ever going to touch the y-axis, no matter how negative my x is, going to negative infinity. I'm never ever going to touch the x-axis. So my asymptote is y is equal to 0.